Okay, so we're going to start talking about statistics. The class is literally called Modern Statistics, right? So I guess that's a good place to start. And I think I'm going to leave it up to you guys. What do you guys think when I say the word statistics? Like what words kind of float into your head? Data. Data is really good, right? So there's a lot of data in statistics. Oh my gosh, statistics. All right. Any other ideas? Yeah. Percentages. There's a lot of percentages in statistics. That's a good one. All right, what else? Ooh, there's a lot of charts, right? We're actually going to spend a whole section on those. All right, any other ideas? That kind of covers it. Yeah, I can think of more, but when I think of statistics, that's usually the thing that happens, right? When people talk about statistics on the news, they usually show you data, they show you percentages, there's a lot of charts and pictures. But, you know, as a math teacher, when I think of statistics, I kind of think of more something different. I think of answering questions. Questions like, what's the average temperature in Salisbury, right? That could be answered with statistics. Who will win the election, right? There's a lot of statistics that go into figuring out the winner or predicted winner of an election. The problem with these questions, though, is you can answer those questions in different math classes, right? The average temperature in Salisbury. You can actually answer that using different types of math. For example, algebra, right? Or geometry or calculus. There are other math classes that can answer complicated questions like this. So, well, what makes statistics different than like an algebra class? What makes statistics different? Yeah.
Isn't it more about like explaining the data and not like solving problems and using equations as much as you work with algebra?
Yeah, that's perfect, right? It's more about taking data and explaining it. And well, algebra is more like, here's an equation, solve for X, right? So what I would explain this as is statistics is a little bit more experimental, right? It's more sciencey than a traditional math class, which is why a lot of students actually like statistics more. So I would say this is more experimental. Okay, and it's more of a science than other math classes. And that's what separates statistics from all the other math classes that you can take here. Okay, so I have some definitions. I don't really care if you can perfectly say what the definition of statistics is, but it really is the science of taking in all this data, right? Collecting data, and then going back and using that data to describe things or to draw a conclusion or make a prediction out of all the things that you have collected. Okay, so that's the idea behind statistics. Now, how do we get that data? We usually take a sample from a population, right? So a population is usually like a big thing that we're interested in. And a sample is like a small slice out of that big thing that you're actually trying to get data from, okay? Now, I am more of a visual person, so I'm actually going to draw a picture of what I think a population is. So let's say a population is like, I don't know, like a birthday cake, okay? And let's say this birthday cake is like one of those square ones you get from like Sam's Club, okay? Not the circle ones. Okay, so this is I'm not very good at drawing today. That's good enough. All right, this big square or rectangular prism is my population. Okay, so every single molecule in this birthday cake or in this big prism is my population. Okay, now when I take a sample from my population, I think of the term cross section. Does anyone know what a cross section is?
If you'd like to basically, in this case, a knife, you just like strike through it. That's the part of the graph.
Yeah, perfect, right? A cross section is almost like a slice of the cake. It was like really tiny. So I'm actually going to draw this. Okay, so let's just say I went right through the middle. Oh, this is bad. There we go. This little slice is called a cross section. Okay, and if the population is the entire cake, this little square or the cross section is my sample. Okay, now what's the, sorry, I'm jumping ahead of myself here. I took the cross section right in the middle of my cake. Didn't matter where I took my cross section out of? Could I have taken it like towards the front of the cake or towards the back? Yeah, right, because every cross section, every single square in this birthday cake is gonna look identical. It doesn't matter if I take the cross section from the back of the cake or from the front of the cake. The cross sections are all identical in this example. Now, does that describe every single sample in the whole world? No, why not? Like, for example, if the school is the population and I took this class as my sample, what problems would arise there? Yeah, it's a pretty small school, yeah. There's a lot of, I looked at the roster, I think there's a lot of business majors in this class. Yeah, so if I asked everyone in this class, like, are you a business major? There'd be a lot, and that's not a good way to describe this whole school, right? So a big word that I want to throw out here is the term representation. Okay, if I asked, or if I made a sample to figure out if who was a business major, or what percentage of the school was a business major, choosing this class wouldn't be a good sample of the population because it wouldn't represent the population, right? Representation is something really, really big in sampling. It's something that we strive to have. We strive to have a sample where it doesn't matter where you take your sample from. Okay, now there are some things that are always kind of important to represent in a sample that a lot of people pay attention to most of the time, like age, race, like gender, things like that. All those are things that we really try to have represented in most samples, but there's other things that can't really be paid attention to as much. There's always going to be a problem with representation because there's all these little differences between every single person or individual in any sort of sample. So representation is something that we strive to achieve, but it's nothing that we can perfectly obtain, okay? So the way we try to achieve a good representation in a sample is we have these things called sampling techniques. So we have techniques that we use to create a representative sample. Before I even talk about these representative or these sampling techniques, I do want to kind of just talk about why we even sample them, okay? So I guess why we even bother with sampling, okay? For example, if I wanted to sample the entire school, I could go and ask every single student in the entire school the same question, right? Why don't I just sample the whole population all the time? Takes too long, right? It takes a lot of time. I'm gonna write time consuming. It really does take a lot of time to go to every single student in the whole school and ask them the same question. Any other ideas why we don't just sample the entire population? What if my population was the entire world and I wanted to ask every single person a question? What problems would arise there other than time? Oh, language barriers, right? So there's a lot of like language barriers. Probably a lot of logistics there too, right? You can't just fly to every single country and ask every single person a question, right? So logistics. It would be kind of expensive too, right? It'd be really expensive to sample every single person in the entire world. So it's very expensive. Okay. Now, there actually is a time where we sample the entire population in the United States. Does anyone know what that's called? The census, right? There's actually a huge organization called the Census Bureau that actually tries to sample every single person in the entire population. Now, we will talk about problems with the census a little bit later, but sampling the entire population is called a census. Okay. Now, census is not like particular to the United States. It can be any population. For example, if my population was the class, I could take the census of the class and ask everyone the same question. Okay, so census is not just for the United States. All right. Now, okay, we can't take a census because it's time consuming. There's language barriers. It's really expensive. So instead, we're going to try to achieve a representative sample by using these things called sampling techniques. Okay, and that's what we're going to do on the next page. All right. So if you flip your notes to the next page, we're going to talk about the most basic type of sampling. We have several sampling techniques, the most basic of which is called a simple random sample. Okay, simple random samples are exactly as they sound. They're random. They're conducted using some sort of random way. Okay. Now this definition, it's a little bit too early to start throwing variables at you. Whenever I see like n or something like that, I just cross it out and replace it with a number like 3. Okay. So a simple random sample of size 3, for example, is a sample where every collection of 3 population items is equally likely to make up a sample. So if I wanted a simple random sample of size 3 of this classroom, I would randomly choose 3 students to create the sample. Okay. Any ideas on how like simple random samples are normally taken, or like how we go about getting random people? All right, so if I wanted to have a simple random sample of like 1 person in this class, what I do is I'd number my roster. So I'd take your list of names, I'd number them like 1 to 31. Okay. I go to Google and type in random number between 1 and 31, right? So whatever number it gives me out, it would tell me which student was the random person. So that's usually how simple random samples are created. Okay. So I think I'm gonna go a little bit overkill here. You're gonna think I'm trying to trick you, but I'm really not. Let's just go through a few examples of if something's a simple random sample or not. Okay. All right, we got a physical education professor. She wants to study the physical fitness of all these students at our university. There's a lot, 20,000. So she obtains a list of all 20,000 students, numbers them from 1 to 20,000, uses a random number generator to generate 100 random integers between 1 and 20,000, and then gets them to answer the questionnaire. Who thinks this is a simple random sample? Hey, you got some hands. I'm not trying to trick you. It actually is. Because, well, she randomly or used a random method to figure out some people to ask in the site. Okay, so whenever there's the word random in it, it's probably a simple random sample. Okay, so yes, this is a simple random sample. Okay, this one's going to be a little bit easier. The professor in the last example, now she wants to draw a sample of 50 students out of all her classes to do this questionnaire. Okay. So instead of doing the random number generator stuff, she's like, hey, my 10 a.m. class is 50 students. I'll just use the first 20 minutes of my class to have them fill out the questionnaire. Who thinks this is a simple random sample? Who doesn't think this is a simple random sample? Yeah, most of y'all raise your hand. All right, this is not a simple random sample because, well, she didn't use a random method to get students in her question to fill out their questionnaire. She just was like, oh, my 10 a.m. class is convenient. I'll just do that. All right. Any questions on simple random samples? Let's flip our page. We'll talk about another one that isn't too important to me. So sometimes there's times where we either don't have like a random number generator, so we don't have like Google to give me a number, or it just wouldn't be convenient to have a simple random sample. And I'll give you an example. Okay. Let's say I have a large pile of really heavy bricks on the floor. Okay, so there's this big pile of bricks. It goes all the way to 0. They're numbered from 1 to, I don't know, 1,000. So that's 1,000 bricks. And then I get Google to tell me where the brick is. And Google says there's a random brick and it's all at the bottom of that pile, right in the middle. You have to dig through the pile and you have to pick one piece of brick out of there, and that's the brick in your sample. Am I going to do that? No, right? Because I would have to move all the bricks aside to get to the one random brick that I want, and that would take too much time and it wouldn't be very convenient. Okay, so in that example, I might just take 5 bricks off the top, and that's my sample, right? It's not the best type of sampling, but it's convenient for me, and well, that's the best I got. So sample convenience is an example of this, where there's no well-defined random method to create my sample. So there's no random number generator, or there's no good way or method that I'm following to get something. It's just convenient for me. Okay. Now, samples of convenience aren't very good, all right? That's all I really want to say about these. I have an example, but it's about the bricks, and I already talked about that. All right, any questions on sample of convenience? All right, let's do something a little bit more fun. Next, we're going to talk about a different type of sampling that you probably haven't heard before. A lot of these sampling methods have really weird names, and they kind of aren't very talked about that much. So I'm going to try to give you ways to memorize these, to be able to understand what they mean, and give you a lot of examples of what this actually tells us. Okay. All right, our first one is called stratified random sample, stratified random sampling. And it comes from this word called strata. Strata. Okay, does anyone know what strata is? Has anyone driven to West Virginia? And as you're driving down the road, you look to the right, and there's like this huge cliff next to you, right? And on this cliff, you'll see like different layers of rocks. So there's like a layer of red rock, there's a layer of gray rock, there's a layer of like bluish rock, and they're like different layers of rocks. Has anyone seen that? Yeah, let me draw it out for you because I feel like this will make more sense. So I'm a visual person. I'm going to take a little bit of this box to draw my cliff with a couple of layers. Okay, the bottom layer is going to have this dotted rock on it. Okay, this cliff is going to have straight rocks, and maybe this one has checkered rocks. Okay. So as you're driving down the road, you see something like this. Probably doesn't look like that, but you'll see layers of different rocks. These layers in a cliff are called strata. Okay. So strata are the layers of rocks. Okay. And well, they're called strata because each layer of rocks shares certain properties. Okay. So maybe the bottom rock is, I don't know much about geology, but maybe it's like an igneous rock, right? And then the next, actually, I think all the rocks have to be sedimentary. You know what? That's okay. The bottom rock is like red, and then the middle rock is blue, and the top rock is gray. They all share the same qualities together, okay? Now, let's see how this goes in a sample, okay? Now, further in this picture, I'm just going to draw a big box to represent my population. Okay, so let's make my population this big box. Okay, and from this population, I'm going to draw a smaller sample. So my sample is here. Okay. Now let's just say in my population, I have strata. So I have groups of things that share a certain quality. So instead of rocks, maybe I have a bunch of squares. So a bunch of squares in my sample. Okay, so that's one group in my sample. Maybe I have like 2 triangles. Okay, maybe I have a bunch of circles, like 10 circles. Maybe 11. Okay, and then maybe I have, I don't know, 3 stars. So if you take a look at the population, within my population, I have these groups, and within each group, everyone kind of shares a similar quality. So they're all squares, or they're all triangles, or they're all circles, right? So they all share a certain property. When I take my sample, which is smaller than the population, I'm going to conserve, well, everything that I can about the population. So in my sample, I'm going to take a random sample of squares. Okay, there's a lot of squares in my population. Should I have a lot of squares in my sample? Yeah, right, because I want to represent the population. So if I have a lot of squares in my population, I'm at least going to have more squares than triangles in my sample. Okay, so if I have 4 squares in my sample, I should have less than 4 squares or 4 triangles in my sample. Okay, if I have a lot of circles in my population, I'm also going to have a lot of circles in my sample. Some might have, I don't know, 5 circles or 6. If I have a medium amount of stars in my population, I'm going to have a medium amount of stars in my sample. Okay, so the idea behind stratified random sampling is we have different groups of things in our sample. They all share a certain quality. And like if I have 40% squares in my population, I'm also going to have 40% squares in my sample. So we're conserving the percentages in our population and in our sample. Does that kind of make sense? All right. Now, I gave you a silly example with squares and triangles and stuff. Let's do something like in real life that actually has numbers attached to it, okay? Okay, so let's say we have a company. There are 800 full-timers and 200 part-timers, okay? Whenever I do something like this, I always draw a picture because it makes a little bit more sense to me. So let me just draw out my population. This is my population. Within my population, I have 800 full-timers, so FT for full-time. And on the bottom, I have 200 part-time. How many total employees are there? 1,000, right? Because I added 800 plus 200. So there are 1,000 total. Okay. So from my population, I want to construct a sample. Okay. And instead of 1,000 people in my population, my sample is only going to have 100 people. Okay. Okay. Now, I made a little mistake when I wrote up these notes. I didn't mean to tell you how many full-timers and how many part-timers there are. So I'm just going to kind of scratch them out and pretend we didn't see it. Let's try to figure out how many full-timers and how many part-timers there are. Okay. So in order to do this, the idea of stratified random sampling depends on like the percentages that there are in the population. So maybe what I should do is figure out what percent of full-timers there are in my population, because that's the percent of full-timers there are in my sample. Okay. So let's actually just calculate the percentage of full-timers. How can I calculate the percentage of full-timers in my population? 800, which is like the thing we want to find, divided by 1,000, which is the total. Good. Okay, so I'm going to take 800 full-timers. I'm going to divide by 1,000. And if you divide this out, you're going to get 0.8. Does that make sense? Cool. Okay, now this decimal might actually be more useful to us in this example, but just to kind of test you on this, how do I turn 0.8 into a percentage? Times 100, perfect. If you ever forget, the word percent is literally per cent. The word cent or 100 is literally in the name. So if you multiply by 100, you'll get 80%. Okay, so I know that 80% of my total is full-time. Okay, so if I know that 0.8 or 80% of my sample or of my sample has got to be full-time, all you have to do is take your percentage, 0.8, multiply it by how many there are in the sample, okay? In the sample. And if you multiply those together, you're going to find out that there are 80 full-timers in your sample, okay? So you have 80 full-time people in the sample. Does that make sense? All right, see, we do a little bit of math first. Okay. Now I could do the same process. I could do like the percentage and multiply it by 100 to get how many part-timers there are. Is there an easy way to figure out how many part-timers there are in the sample? What is it? Perfect, right? You just take 100, subtract 80. Because there's 100 total, and we already found that there's 80 in the other half, so there's got to be 20 part-timers in my sample. Okay. So that's basically how people go about doing a stratified random sample. They basically figure out the percentage in each population, or of each of the groups in the population, and they calculate how many are in the sample this way. All right. Any questions on stratified random sample? All righty. Well, this is where the last class ended up, so I guess I'll let you out a little bit early. It was very nice to meet you today. I don't know, I'm excited for the semester. I'll see you on Wednesday.